So we shall do the problems now. Problem number 9. Consider two x bar distributions corresponding to the same x distribution. What that means is we are taking two situations. In both of them, the mu and sigma, they remain same. But in one of them n equals 100 and the other one n equals 225. So n equals 100 versus n equals 225. They are asking which x bar distribution has smaller standard error. This is a term which you will be hearing more often now. So what's standard error? It's simply sigma divided by square root of n. So we know that, but by the way, we can check both this is bigger than equal to 30 and this is bigger than equal to 30. So we can apply CLT. So x bar follows normal with mean mu, and the standard deviation of x bar is sigma by square root of n. So the standard deviation of sigma is standard error. You can simply remember sigma by square root of n. All right. What they're trying to ask is what happens when you change n. So that's a simple thing. If n goes up, obviously square root of n goes up. And that means sigma by square root of n goes down. Like in a fraction, if the top of the fraction remains the same, that means sigma remains the same, but the bottom of the fraction goes bigger, that means square root of n goes bigger, then the fraction becomes smaller. So, and this is something we will be using quite often now, this fact. If n is bigger, then standard error is smaller. So obviously n equals 225 has smaller standard error. Now, although they are not asking for this, but we know from the class, if we go to my website, so we know that if we shift mu, keeping sigma same, so if we keep the standard deviation same and take mu to the left, the density goes to the left. If you take mu to the right, the density goes to the right. But suppose you keep mu fixed at something. Actually, let's keep it fixed at 0, for example. Then if you decrease sigma, make sigma smaller, it becomes skinny. If you increase sigma, it becomes flat. So small standard deviation, skinny and tall, large standard deviation, short and flat. So if sigma by square root of n goes down, that means the standard deviation for this normal curve is going down, which will mean it will become skinny and tall. So we shall be using this in the next few problems. Now, look at question 11 or question 12. These are both same kind of questions, and we shall learn the theory and deal with these questions. So the theory is, okay, so in these problems, it goes like this. The mu and sigma are given and they're like fixed. Mu is given as something, sigma is given as something, and they're fixed. And they have given one value of n, a small value, and a big value. So they are asking probability x bar lying between two numbers a and b, or probability x bar bigger than a number. For example, in question 12b, it's probability x bar bigger than 6. And in question 11, it's probability x bar lying between two numbers 15 and 17. So what happens to those guys? So I mean, we can learn these problems individually, or we can learn the general theory behind it and hence attack the problems. So we shall start with the tails. As I told you guys, so here mu and sigma remains fixed. Mu and sigma are fixed. But there's a big value of n and a small value of n. And we learned from the previous page, if n is big, it's tall and skinny. If n is small, it's short and flat, as we see on this picture. And observe this point B. What's B? B is just any number to the right of mu. B is any value bigger than mu. There's nothing special about B. Okay. Given such a number, we are asking the question, what happens to probability x bar bigger than b? Like for the small value of n and between the big value of n, between the small value and the big value, how does this probability x bar bigger than b change? Now, probability x bar bigger than b, we shall call it the right tail. You can guess why. So you can see from this picture, for the n small, that means the short and flat graph, the right tail is red plus blue. I mean, I cannot show this to you. You have to take a good look at the picture and then you can see it in 5 seconds. Just take a good look at the picture and see for the shorter tail, it's red plus blue. And sorry, for the smaller value of n, that means for the shorter graph, short and flat graph, it's red plus blue. And for big N, this is a skinny graph. For the skinny graph, it's only blue. So, and in this table, I have written just that. So for n small, the tail is blue plus red, and for n big, the tail is just blue. So what do you think? Blue plus red is bigger than blue, right? I mean, that's obvious. Blue plus red is bigger than blue. That means the tail is big for n small. Now you may be thinking I cheated a little bit there because the value of b that I'm using, that's to the right of this point. So at this particular point, these two curves meet and b is to the right of that. So maybe something will happen to the math, the mathematics will change if I take b somewhere here. Maybe I cheated somewhat. So let's take an example like this and show you. So once again, there's a n big, there's a n small, just as before. There's a tall and skinny graph, there's a short and flat graph. And now the intersection point of the two graphs is around here, and my b lies to the left of that. Obviously b is still bigger than mu. That has to be there. And obviously, as before, we are looking at the right tail. But now the position of b has changed. So look at the skinny graph. That means for n big. For the skinny graph, the right hand tail is blue plus red. And for the flat and short graph, that means for n small, it's blue plus green. This I cannot explain anymore. You have to observe it. That's all. It's clear from the picture. So now we are comparing between blue plus green and blue plus red. Now let's just do the following. So can you see that red is smaller than green? That you have to observe from the picture. If you agree with that, that will mean blue plus red is smaller than blue plus green. That's basic algebra. And hence we have blue plus green is the bigger one, and that's for smaller n, n small, blue plus green. So once again we have the same result. So for smaller value of n, the right tail is bigger. Here also, for smaller value of n, the right tail is bigger. So by shifting the position of b, we have changed nothing. The result still holds. Of course, I can do the same thing for the left tail, but I am not, because the left tail and the right tail are mirror images of any other. Like, I'm not explaining this too much. So suppose I have to prove that the left tail is bigger for small n, but you can see that both the skinny graph and the short graph, they are centered around mu, and they're symmetric. So whatever happens for left tail also happens for right tail, and vice versa. So I'll leave it at that. And I'll state my general result as follows. If n is big, then tails are small. If you remember this, then you'll be good. Actually, we just proved the opposite. I mean, if you want, I can state that. So we kind of proved that if n is small, tails are big. It's the same thing. Okay. Now comes the next part. So here we are dealing with the middle portion. We are not dealing with a tail. So we are dealing with the middle portion. What do I mean by middle portion? I mean so here is mu. There's a number A left of mu. There's a number B right of mu. And we want the area between A and B. So we want probability x bar lies between A and B. This guy. This is not a tail anymore. This is a middle portion. Now I can do the coloring thing once again. I can do the whole proof by coloring. But let me use some logic. Let me use this result and let's put it to good use. So you have to agree that probability x bar lies between A and B means 1 minus probability x bar bigger than B minus probability x bar less than A. Why am I saying that? So look at this. So suppose you can see the number A, the number mu, the number B. So x bar between A and B means the green portion. That's the middle region. X bar bigger than B, I've shown in red. And x bar smaller than A, that's like the blue. Now, the blue, the green, and the red, they make up the whole region. So the total probability is 1. That means 1 equals probability x bar less than A plus probability x bar lies between A and B plus probability x bar bigger than B. So the left tail, the middle portion, and the right tail make up the whole region. Hence, if you add their probabilities, it will be 1. And from there, it's easy. You take this one to this side, and also this one to this side, and they both become minus, as here it becomes. And you get it. That's it. Nothing else is going on. Okay, so we have proved this. Now, my logic is as follows. So if n is smaller, then the tails are bigger. This we already know from here. If n is small, tails are big. So if n is smaller, this tail and this tail, they are bigger. Okay, so let's look at this expression. So okay, sorry, I wrote the notes in opposite. So the thing I want to claim is, if n is small, the middle portion is small. And we prove it as follows. If n is smaller, then the tails are bigger. That means 1 minus right tail, 1 minus right tail minus left tail should be smaller. It's just like saying, if a number goes bigger, then the negative goes smaller. So it's like this. If 7 is bigger than 5, I mean 7 is bigger than 5, then minus 7 is smaller than minus 5. It's just like that. So if the right tail and the left tail both goes bigger, then 1 minus right tail minus left tail, that becomes smaller. That's my logic. And if that happens, that means this guy goes smaller. And hence we have proved what we want to prove. We will see a slight exception, but the exception will not be a big deal. Now, what I'm talking about is this. So, okay, so that's my badly drawn picture. Actually, it's really bad. Sorry. Sorry for that. Let me copy and paste. Okay, so obviously we know that this is n big, this is n small also. So I'm doing this in advance for question number. Okay, I know that we'll do this question later. Actually, it's question number 11. So I told you x bar lies between two number a and b. Now here a is 15 and b is 17. But in my examples, a was smaller than mu. But here a is mu. Mu is 15 and a is 15. So that should not create confusions, and that's why I'm doing this. So suppose this is like obviously mu, and this is like numbers b bigger than mu. So for question 11, it's x bar lying between mu and b. But we have a way to deal with that too. What I'll do is I'll write probability x bar bigger than mu equals this plus probability x bar bigger than b. So what I've done is, this is mu and everything right of mu. I've divided in two portions, this portion and this portion. So probability x bar lying between mu and b, that's this portion, and probability x bar bigger than b is this portion. I've divided it into two parts. Now since x bar is normal with mean mu and standard deviation sigma by square root of n, so probability x bar bigger than mu is 0.5. So let me just write here as 0.5. So if that's true, then probability x bar lying between b and mu is 0.5 minus probability x bar bigger than b. Now everything's clear. So now let's just follow the logic. So if n is small, then probability x bar bigger than b is big, which means 0.5 minus probability x bar bigger than b is, it's this guy, is small. Okay, so that's a slight detour we took, but look at this. Is it really hard to remember? Let's see. So here we claimed if n is small, middle portion is small. And in the next example we did, if n is small, this probability is small. So this probability between mu and b is strictly not a middle portion, but it kind of is. I mean, it's not probability between a and b. It's not. It's between mu and b. But, I mean, it kind of is. So it's not that hard to remember for you. So the only things you guys need to remember is this line, if n is small, middle portion is small. And this line, if n is small, tails are big. So let me write those down. If n is small, tails are big. But middle portion is small. So if you remember that, all these kind of problems are easy. So let's have a look. So question 11, mu 15, sigma 14. You have to find like probability x bar between 15 and 17. We are comparing between n equals 49 and n equals 64. So all the details of the calculations you can see like in the notes. But my interest is, why should you expect probability of part B to be higher than part A? So in part B, n is 64 versus in part A, 49. So if n is small, the middle portion is small. This we already know. I mean, that's not a mystery to us anymore. So we know if part B, n is big, so middle portion is big. That's all. Just a similar kind of thing happening, but with a little interesting twist. I mean, question 12 you can do. It's the same kind of thing going on. But question 15, slightly more interesting. So here mu is 85, sigma is 25. Mu is 85, sigma is 25. All right. And if you read the question, it's normally distributed. So mu 85, sigma 25, and it's normally distributed. All right. So remember, we needed n bigger than equal to 30 or normally distributed. Obviously, I mean, you have to write it more nicely, but it was n bigger than equal to 30 or original distribution is normal. That was it. So since in these examples you will see that this does not hold, so we have to lean on this crutch. Okay. So question part A is, what's the probability that a single test x less than 40? Okay, so this is not a CLT problem. Question number part A is not a CLT problem. But the way they are making the question up, it kind of looks like that. So what am I talking about? So suppose we know that x bar follows normal with mean mu, standard deviation sigma by square root of n. Now if n equals 1, that means there's just single x. So if we apply the CLT, that's normal mean mu, standard deviation sigma by square root of 1, that's sigma. But that's exactly not CLT. I mean, you can think of it like this if you want, but that's a weird way of thinking. I mean, that's that's a weird way of thinking. Like, this is how we started, and from that we got the CLT. But now they're showing this result, original result, with the help of CLT. If it helps thinking like that, then you can think of it. But okay, let's do the problem. So x follows normal with mean 85 and standard deviation 25. They are asking probability x less than 40. Usual stuff, find the z-score, 40 minus 85 by 25. Go to the z-table and find this probability. Sorry, I mean, yeah, 40 minus 85 by 25. That's minus 45 by 25. So minus 45 by 25 is minus 1.8. Is 0.0359. And 0.0359 is the correct answer. I do not know why I pointed this arrow. Sorry. Let me actually draw a line so that there's no confusion. Next problem, n equals 2, find x bar less than 40. So this is just a typical CLT problem. X bar follows normal with mean mu equals 85 and standard deviation sigma by square root of n. Obviously sigma is now 25. I'm sorry, sigma is 25. 25 by square root of 2. 25 by square root of 2 is 17.6776. And that's what I wrote. And if you do the usual stuff, find the z-score minus 2.55, and then go to the z-table, you'll find 0.0054. And you can continue doing these things. I mean, that's fun. But let me go to the question. So for part B, it's n equals 2. For part C, it's n equals 3. For part D, it's n equals 5. Now, I haven't done part C or part D. I mean, if you want to do it, you can do it. Okay. But the interesting part is question E. So compare your answers to A, B, C, and D. Did the probabilities decrease as they increased? So what should we expect? So from our theory, what should we do? So for part A, n is like 1. For B, it's n2. For C, it's n3, and then n5. Okay. Now we are talking about probability x bar less than 40. And that's a left tail. Alright. So what have we learned about what happens to tails? If n is small, tails are big. So here n is like smallest, and it goes up to here. So I mean, here n, like the tail should be biggest. If n is small, tails are big. So for part A, it should be biggest, and for it should go down up to D. That's all. I mean, we need nothing more. You can see this already happening from A to B. For A, it's 0.0359, and for B, it's 0.0054. So it has already gone down from A to B, and you'll see it's going more down if you do part C and D. And that's it. So that's why it's fun to learn a general theory. You can do these problems. I mean, just learn it once and it will apply everywhere.